Okay. So yes, thank you all for joining us for this CES EDI seminar. Thank you to Abdel for taking part. I'm going to do a brief introduction and we'll take it off to him. So Abdel Zayed is a PhD candidate at Mila, working with Prof. Sarath Chendar. His research interests include natural language processing, fairness, and causal inference. More specifically, he is interested in understanding why language models can be biased against certain groups based on their gender, race, sexual orientation, or religion. We'll be hearing about more of that very shortly. He also works on developing new methods to mitigate these biases. He received his master's in electrical and computer engineering from Concordia University under the supervision of Prof. Hassan Ravaz, and he holds a bachelor's in electrical engineering from Cairo University. Abdel, I'll turn it over to you. Thanks so much.
Thank you so much, Matthew, and thank you for inviting me. So hi everyone. I'm Abdel, or Abdelrahman, as you wish. I'm a PhD candidate here at Mila, and today I'm going to be talking about our work on gender bias reduction. So our work has just been accepted in AAAI, so it should be out very, very soon. We will put it on archive, but for now it's not. So it will be out in a few days, I hope. So our work had the following title: Deep Learning on Healthy Data Diet. And I can imagine that for you, you might not really know what we mean by healthy data diet by just seeing it. But one way of just summarizing the work, if I have to summarize it in 2 sentences, you can think of data diet as pruning. So when we say data diet, it means that we are proposing a method that prunes the data set. And if you think of the word healthy, it means that this pruning is made such that you keep the examples that are important for fairness, and you remove the examples that are not important for fairness or are even harmful for fairness. This is just, if you want to summarize this work in 2 sentences, this is how I would say it. Of course, you will see the details, but just a quick overview, we are proposing such a method that looks on the data set, and if there is an example that is harmful or useless for fairness, we don't need it. But if there is an example that is important for fairness, we keep it. So it's a data diet that is healthy. So let's get into the details of this work. Of course, before I start even talking about the agenda, I really encourage everyone to ask during the presentation. I really love being asked during presentations. I don't know if you have a rule that people ask after the presentation, but I personally prefer being interrupted and ask, because I don't like when it's a one-sided presentation, because I think it's always better to have interaction. So yeah, I might not be able to see hands being raised, so you can unmute yourself and ask if you want. So my agenda for today is going to be, I'm going to start by talking about gender bias. So just an introduction to what gender bias is and how exactly we define gender bias. And then I'm going to be talking about the different bias mitigation methods that exist. Not all of them, of course, I'm not going to cover all of them, but for sure, I'm going to cover the ones that are related to our work. And I'm going to comment on why we think these methods are missing something, and this is why we are going to propose our method. And then, of course, we're going to talk about the results and the conclusion. Also, before I start, I have to thank all of my collaborators. We have this work in collaboration with Prasanna, who was at the time at Mankil, and Gonzalo, who is a postdoc at Mila, Hamid from Microsoft Research, my supervisor, Sarath Chendar, and of course, Samira Shabanian from Microsoft Research, who's my mentor also in Microsoft, and she's also here with us. So thank you, Samira, for coming. Yeah, let's start talking in more details. So we're going to start by just defining gender bias, so that whenever you see this word, because you will see it again many times throughout the presentation, I just want to be clear on what I mean by gender bias. So if I have a machine learning model that is, let's say, used for classification, which is our focus in this work, gender bias is the tendency of the model to change the predictions when the gender words in the sentence change. For example, if you are doing sentiment analysis and you give your model a sentence that says, this man has a smile on his face, and you get a probability of happiness of 0.9. Then you change the sentence to, this woman has a smile on her face, and you find that the prediction became 0.1 probability of happiness. That doesn't make any sense, because whether or not the person is happy is not related to the gender. So it seems that the model is learning some correlation between gender worth and output labels. And this is why it's biased. So this is how we define a biased model. This should not happen. The predictions should not change by changing the gender worth. And I actually don't think I should actually convince you that why this is not desirable, because I think you already know why this is not desirable. So imagine if you are using a model for resume filtering, for example, you have a company and there are 200 people applying to you and you have all of these resumes, and you decided just to use a machine learning model to filter them, just so that you have at least, let's say, 20 resumes to look at instead of looking at the 200 resumes. If this model is biased, it will exclude people who are as qualified as other people who were not excluded, but just the difference between them is just the gender, which is, of course, very, very dangerous. So we don't want this to happen. So again, what I'm trying to say is that models bias means just changing the predictions by changing gender worth, and for sure it's not desirable. So the question of whether or not it's desirable is, of course, kind of obvious, but the other important question is, how do I mitigate bias? So in the literature, there are many categories of methods that deal with this problem. There is the category of method that we call data-based, which actually change the data set. So they add examples or remove examples or change the examples such that you end up having a data set such that when you train on it, your model will become less biased. For example, you find that there is a specific gender that is underrepresented. You add more examples talking about this gender in the data set so that overall the model becomes less biased after training. But you don't touch the loss function. This is only data-based. You only change the data set. There are other methods that we call regularization-based, and these methods actually do change the loss function, but they don't change the data set. So if your loss function was, let's say, cross entropy or any other loss function, you are going to add an auxiliary term that teaches the model not to be biased. So it's just a penalty that the model gets when it's biased. So overall, the model is not just learning the task, it's also learning not to become biased. And there are adversarial-based methods that use adversarial training for bias mitigation as well. Every category of these is just many methods, not just one method. But in our work, we are focusing on the data-based methods. We have explored the other methods as well in other projects, but for this project, we are focusing on the data-based methods. Are there any questions before I start?
Yeah, you asked people to interrupt you, so I'll interrupt you.
Yeah.
So for this regularization-based method, where you can just say like, okay, don't change the prediction based on gendered terms, basically. Why is that insufficient?
Why is that insufficient? So
why do we need these database methods? If we know what the human bias looks like, can't we optimize directly for that?
Yeah, because the bias is not just coming from, so when you have a pre-trained language model, let's say BERT, this BERT undergoes two different steps before being used for classification. There is the pre-training step, there's a fine-tuning. Even if you do all of these things during fine-tuning, there is still a bias that had been learned during pre-training. So even if you try to do your best to make it not biased during fine-tuning, the model still had learned some bias during the pre-training. So you will for sure have some improvement because of doing this and adding the auxiliary term and all of these things, but it will not just get the bias to zero. It will not get it to zero because the model had already started by being biased. So this will be shown in more details in one of the slides that shows how exactly the pre-trained model, the different phases that it passes by before being used for classification.
So then one more question. If this is in the future, I won't ask further on this, but then is the assumption, apologies, is the assumption here that you're using a pre-trained model?
Yes.
Okay.
Yes, that's true. I'm assuming that I'm using pre-trained models. So all of the results that we have in this work are on pre-trained language models, BERT, Roberta, all of these family of models.
Got it. Cool, thanks.
Thanks for asking. So I'm gonna cover some of the database methods, and then we're gonna talk about our work. So the very first method is called counterfactual data augmentation. It's also the most famous one. So it's very, very simple and straightforward. For every example that you have in your dataset, let's say you have this example that says he's a doctor. You want to teach your model that being a doctor is not attributed to one gender. So you create what we call a counterfactual sentence, such as she's a doctor. So you flip the gender words. And now both sentences are going to be included in the training data. So that the model is not only seeing he's a doctor, it's seeing both. So the model should learn less correlation between being a doctor and being a he. It is now seeing both of them. And you will keep doing this for every single sentence that you have in the dataset. So if you have 1 million examples, you will have 2 million. 1 million is the original examples, which we sometimes call factual examples, and 1 million as the counterfactual examples. So overall, you will have 2 million. So for sure, it is increasing the training time, but it has been proven to work effectively in bias mitigation. So briefly, it is augmenting the data set with counterfactual examples. That's why we call it counterfactual data augmentation. And the abbreviation for it is CDA. So whenever you hear me saying CDA, this is CDA. There is another method called counterfactual data substitution, and it's also very similar to counterfactual data augmentation, but there are some differences. So again, you have the sentence, you create the counterfactual, but here you don't include both of them. You have a probability of 0.5 of including the first one and a probability of 0.5 of including the other one. And the reason why you do this is that you think that if you include both of them, you are increasing the training time. But in this way, you are still adding some counterfactual examples while not increasing the size of the data set. So it is a substitution. It's not an augmentation. So imagine you flip a coin. If it's head, you include the original one. If it's tail, you include the counterfactual one. So to summarize some of the existing methods in a better way, we can say that we have the factuals, the factual examples, and the counterfactual examples. And if we put them together, we get CDA, which I have just described, which is just putting them together. And this is my new training dataset. If I put half of the factual sentences and half of the counterfactual sentences, I call it CDS, or counterfactual data substitution. We are thinking in this work of a different way of combining the original examples and the counterfactual examples, such that it outperforms CDA and CDS. This is the main research question that we have in this work. Does anyone have any question on that, or is it clear what exactly we're trying to do? No? Okay, good. So we think that in order to outperform these methods, we need to understand very well where exactly the bias is coming from, which is also related to Matthew's question. So if we understand where exactly the bias is coming from, we can come up with a maybe different method that can also outperform that. So like I said, we are working with pre-trained language models. And the way pre-trained language models are trained is as follows. First, you start with the pre-training. And this is the very first phase that you have. You have two phases. The first phase is called pre-training. And in this phase, you just learn language modeling. You don't learn any task. You try to teach your model to get realistic probabilities given some history of words. So here I'm telling my model the volcano is about to, and the model is supposed to predict the coming word. So the model had seen the word erupt many times with the word volcano in the same sentence. So if you maximize likelihood, you will find that erupt has the highest probability because we've never seen volcanoes walking or running, but we have seen volcanoes erupting. So as you can see in this phase, there is no specific task. The dataset is not labeled. It's an unlabeled data that is used for just teaching the model how to do language modeling. Then, having done that, you save the models, you save the weights of the pre-trained model, and then you go to the fine-tuning. During fine-tuning, you do have a specific task. For example, you are trying to do sentiment analysis, or you are trying to do resume filtering, any task. So here, you should teach your model exactly what the task is. So here I'm assuming that we are doing sentiment analysis. I'm putting my examples, and now the model has to tell me the sentiment, let's say happiness or sadness. So now the question is, where exactly is the bias learned? Is it learned during pre-training or is it learned during fine-tuning? So the answer is that it's learned during both. Because if the data set that I'm using for pre-training has biases, for example, the model always sees the word doctor and the word he in the same sentence, but like very rarely sees the word doctor and the word she in the same sentence. So what's going to happen when you maximize the likelihood is that the model will output a very high probability of a he when the history contains the word doctor, but it will be much higher than the probability of a she. Not because the model is inherently biased, it's just because this is what you get when you do maximum likelihood. This is basically what maximum likelihood is. So there is a bias that is being learned by the model during pre-training. And there is also a bias that is being learned by the model during fine-tuning, because again, the same problem could happen during fine-tuning. You have a lot of sentences talking about nurses, and every time this is happening, it refers to them as she. So the model again learns the same thing. But the difference is that pre-training is more computationally expensive. So you normally need billions of tokens to train your model on during the pre-training step. During fine-tuning, you normally need less examples. So people normally do the pre-training once and they don't change it, and they can change the fine-tuning based on their task. So that's why I was saying that even if you are doing your best during fine-tuning, you are still starting with the biased model. The model is already starting from a point where it is biased. It had learned some biases during the pre-training step. So is it clear where exactly the bias is coming from, and how, from our point of view, where exactly when the model starts being biased? There is no specific phase that is responsible for bias. They are both responsible for bias. Okay, so you might ask yourself, so what if I use data augmentation that you have just explained? So in the pre-training, nothing will change, because like I said, you do the pre-training and you save your model, then you can change the fine-tuning as you want, but you could change the pre-training, but it's very computationally expensive. So if you are doing data augmentation, you will have a different fine-tuning. So like I said, you will have the factual examples and the counterfactual examples. And if I'm just assuming some sentences, he's smiling, everyone is crying, and so on, and I'm assuming they're counterfactual versions, she is smiling, everyone is crying, and so on. So there is something interesting happening. You are now introducing these counterfactual sentences, and they are making sure there is a balance. This is good, but it is not really taking the bias to zero, because the model is already starting from a point where it is biased. After pre-training, the model had already learned the bias. So you are reducing bias, but it's not zero. It's not gonna be zero, because there is still bias during pre-training. So we think that there are two things that you could do to improve this process. The first thing is that although it's better to add the counterfactuals compared to not adding them. So for example, here, if I add she is smiling, it's better for the model because I'm teaching my model that smiling is not gender related. This is good. But it's even better if you do some pruning. We think that if you do some pruning, you will even have better results. Why is that? So let's take an example. Let's say the model during pre-training had learned that boys are good at soccer. So it had seen this sentence a lot. So the model starts learning that whenever you see the word soccer, then you should use some male pronouns. Then we go to the fine-tuning. Again, the model starts saying boys are good at soccer. So you introduce the counterfactual sentences saying girls are good at soccer. This is good, but we think that it's even better if you remove the examples, if you prune the examples that are saying boys are good at soccer, because you are already starting from a biased model. So if you prune these examples, it will be even better. It's even better than adding the counterfactual sentences. So this is how we can improve this data augmentation. This is the first improvement that we have. The second improvement that we are thinking that actually led to our proposed method is that you actually don't need all of the counterfactual examples. So here I'm showing two examples. The first one is he is smiling and the counterfactual is she smiling. But what about the second one? Everyone is crying, which implies sadness, but the counterfactual is also everyone is crying because there are no gendered words. So there is absolutely no importance of adding the counterfactual sentence. So we are claiming that not all of the counterfactual sentences are important. Some of them are important, some of them are not, and some of them are less important than others. So we think that if you can quantify the importance of the counterfactual sentences, you can get an improvement by only adding the important ones. So to summarize, we're adding two modifications to data augmentation. First, prune some of the examples in the data set to reduce bias. Second, don't just blindly add all of your counterfactual examples, only add the important ones. These are the two modifications that we have to data augmentation. So hence, we propose something that we call healthy data diet. So I'm assuming that these are my examples in the dataset, and I'm ranking them based on importance. I'm gonna be very explicit about what I mean by importance, but for now, let's just assume that we know what examples are important. I start with the ones that are important, and at the very bottom, there are the ones that are not important for fairness. So important here is for fairness. And then again, I have the counterfactual ones. Again, the same, every example has its corresponding counterfactual. And what data augmentation does is that it only just puts them together. That's it. We think that there is something a bit smarter, which is that you don't put them together. You just prune some of the examples in the factual part. So let's say you take A%, where A is a hyperparameter, and this is gonna be the factual part. And for the counterfactual part, you are only gonna take the important ones, because the non-important ones are not going to improve your fairness. If you add the counterfactual of the weather is nice today, this is not improving fairness because there are no gender words. So this is basically the difference between our healthy data type and the counterfactual data augmentation. Two differences, again, you prune the dataset to get rid of the harmful examples, and you only include the important counterfactual examples. Does anyone have any question? Because this is the only slide that has everything, every detail in the method. So if you understand this slide, it's very, very important for me. Yeah.
There's one earlier question in the chat that I didn't have a chance to interrupt you for. The question is, if you start with, I don't know if this person wants me to say their name, so I'm just going to read it out. If you start with an unbiased pre-training model, for instance, exactly half of examples of doctor are of one gender, can bias still happen during fine-tuning?
Yes, bias can still happen during fine-tuning, because in fine-tuning, if you are using some, let's say, loss function that again is teaching the model to learn the likelihood in the training data, and the training data has bias in it, then yes, the model will learn the bias. But it would be like an easier problem for us, because we can actually just do the counterfactual, add the counterfactual examples and get rid of this problem. It would be an easier problem for us. But yes, the model can learn the bias again.
And then I had a question on this. I assume that this is coming up later, but how are you going to automatically detect if a counterfactual is important? Is it just, does it have gendered terms?
This is exactly the coming slide, but your observation is correct.
Okay.
No, your observation is really correct. It is related, it's very much related to whether or not. So at least I think you agree with me on the fact that if there are no gender words, then it's not important at all. This is something that we agree on. But the thing that we might still not know is, among the ones that do contain gender words, what are the ones that are more important than others? And how do I quantify this? So this is exactly the coming slide. But at least I hope you agree on the first thing. Yeah.
Though even detecting if something is a gendered term or not, right? That could be tricky as well, because there could be slang terms, right, that indicate gender that you don't recognize. You have to think ahead of time.
Yes, for sure. So we are using some Python package that detects gender words, but for sure, I mean, it's not perfect. There might be words that are just not going to be detected. So these things happen for sure.
Okay, cool.
Yeah.
I think that question was enough time if somebody else was typing that they could have done that out. So I think we're good to keep going.
Okay. So just one thing I also wanted to highlight is that A and B are hyperparameters. You have your validation data set. You choose the best combination of A and B such that you have an improvement on fairness and also a very small degradation in the performance, because you can also expect that when you prune the examples in the original synthesis, there will be performance drop. So you don't want this for sure. So you set A and B such that there is a performance drop that is not more than, let's say, 2% or 3%. You set it, but you should expect some performance drop the moment you do this pruning. So now going to Matthew's question, which is how do I know the examples that are important for fairness? So we think that the importance of a counterfactual example to fairness is related to the difference between the model's prediction on both the original example and the counterfactual example. Let me give you an example. Let's say my dataset has she's a nurse a lot, and I'm not sure whether or not I should include he's a nurse. So what I should do is that I should get the model's prediction for both the original sentence and the counterfactual sentence. So he's a nurse is going to have some prediction, and she's a nurse is going to have some other prediction. And if the model already knows that there should be no difference, the model will output actually the same output to both of them. And then you know that the model is already not biased and you don't need to add this, he is a nurse. But if the model outputs very, very, very different predictions, then that means that the model is correlating gender and output, and you actually do need to include he's a nurse. So the larger the difference between the predictions, the more important it is to add the counterfactual example. If there is a very, very large difference, it means that the model is having a very, deep correlation between gender words and label, and it's very important that you add the counterfactual example. If there is a very small difference, then the model is close to knowing that there should be no prediction, no difference in prediction, then it's not that important to add the counterfactual. And of course, if you go to this example that's saying the weather is nice today, both sentences will get the same prediction, which is actually saying that there is absolutely no importance, there is zero importance to adding the weather is nice today as part of your counterfactual examples. Does that answer your question, Matthew?
Yeah, that does make sense, and that's clever. While we were chatting, there were two questions that came up in the chat, or while you were saying this. The first comes from a person who says, I joined a bit late. I was wondering how the healthy data set is more fair than using all the counterfactuals.
So if you use all of the counterfactuals, so the fact that you are taking only the important ones is not improving the fairness, it's just making it less training time, but it's not improving the fairness. So the reason why we improve the fairness is that we remove the harmful examples that when we do the pruning. So the fact that we are only caring about the important ones is just not to have, so that we don't have redundancy. This is the reason why we do this. But of course, if you add all of the counterfactual examples, then fairness-wise, it's okay, but it's just a lot of redundancy.
Makes sense. And then there's a second question. Do you perform statistical tests to see if the difference is significant?
Between what and what?
Between, I think, I can be corrected here if I'm wrong, but I think the idea is between the two predictions, between the he is a nurse and she is a nurse, do you see if the change in output confidence is statistically significant?
We have not done, a specific experiment to test for significance, but everything that we are doing is for 5 different seeds. So if, for example, a specific example is seen as important, this is not just an observation on one specific seed. It's an observation that's the average of 5 different seeds. So it's not just a lucky seed that made this specific example important. It's always the average of 5 different seeds. So if there is any randomness happening, it should be reduced by averaging different seeds.
All right.
This is actually a good point because you might run a specific seed and get some scores, then run a different seed and get other scores. So your rankings will change your definition of an important example will be different. So that's why we make sure that we run everything on 5 seeds and take the average so that it's not just the seed that's controlling, it's more of the importance itself.
Cool.
More questions, or should I?
I think you're good to keep going for now. I'll let you know if other chat stuff comes up.
Okay. So I just decided to have some examples and their counterfactual version and just showing you how the GE score looks like. I also forgot to tell you that GE is the name of our score, and GE stands for gender equity. Okay. So here there is an example saying, Kate, you're a stupid woman, and the counterfactual is Kareem, you're a stupid man. And again, you get the difference in predictions, you get the L2 norm. This is how important it is to include Kareem, you're a stupid man. And the very last one, as you can see, there are no gender words. Oh my God, when will this show end? These examples are taken from Twitter. So then again, the counterfactual is the same and GE score is 0, which means that it's not important at all to include the very last sentence in your counterfactual part. Does it make sense?
Okay. It does make sense. I'm surprised that you're swapping out the name swap out is interesting here.
Yeah,
it's not just gender, it's also
we do
culture, right?
Yes, because also names do imply gender as well.
Sure.
I mean, yeah, so anything that implies gender is swapped. Yeah.
Okay. So you said you used a Python library for the gender terms. What are you using for the name swaps?
It is the same Python library. It's called Gender Bender. It swaps every single gender-related word.
Got it. Interesting. Okay.
So for now, for explaining the methods, it's over. We have done that. So now I can go to the results if you are okay with me going to the results. Okay, so our results are basically two parts. The first part is just to verify that GE score makes sense. It's actually capturing what it is supposed to capture. And the second part is just to prove that our method is actually outperforming CDA and CDS that I have discussed in the beginning. So before I show the results, I just want to think of what should we expect to be convinced that GE score is actually capturing? What is the thing that we should see to say that, oh, GE score is capturing the importance? So in my point of view, I think if GE score is really capturing the importance of the counterfactuals for fairness, then if I only include the top 20% with the highest GE score, I should get a very large improvement in fairness that is almost close to including all of the counterfactual examples that I have, because they are the most important ones. But if the GE score is not reflecting the importance for fairness, then even if I take the top 20 or top 30, I'm still very far from the overall improvement that I used to get by adding all of that. This is at least how I see it. Does that make sense to everyone? Is it also how you see it? Okay. So we decided to have this experiment where we are going to add different ratios. So the x-axis is the ratio of the counterfactual examples. Could be 10%, 20%. So 0.2 means 20%, 0.4 is 40%, and so on, up to 100%. And the y-axis is the fairness, and it's here measured by demographic parity, which is one of the fairness metrics. And I'm going to rank the examples based on different scores. Our score is called GE, and there are other scores that exist as well, but they are not for fairness. They are for performance. So there are works that say that you can also give scores to examples based on how important they are for the performance. So you can say, if I want to keep the same performance and prune, let's say, 50% of my data set, which 50% should I include? So they give scores so that you know the ones that are important for performance and you only keep them. So it's not exactly what we are doing. It's not actually what we are doing, but it's just has the same idea of giving importance to examples. So I'm including 3 different scores, EL2N, forget, and gradient norm. Again, they are not really an importance for fairness. They are the importance of the examples for performance, not for fairness. But our score, the green one, the GE score, is the importance of the examples for fairness. So also there's the random, meaning that you just put them in any order and take just 20%. So this is also one of the baselines. So you can see that the green curve is always faster in reaching the highest fairness. For example, if you look on the middle graph, the Wikipedia one, you can almost reach the highest demographic parity by only using 10% of the counterfactual examples, simply because you are using the most important counterfactual examples. And for Roberta, this is for BERT. For Roberta, it's even more evident. So you can see that the green curve, which is when you rank the examples based on the GE score and take, let's say, top 20% or top 30%, you always reach higher fairness with less number of examples, which again, it just confirms that you are actually indeed ranking them based on how important they are for fairness, so that you can reach very high fairness by only, let's say, 20% or 30%, because they are the most important 20%. So I hope we have now verified that GE score makes sense. Now let's go to the second part of the results, where we want to show that this recipe that we came up with of adding A% from the factuals and B% from the counterfactuals is actually better than just the 2 other methods that I talked about, CDA and CDS, which just put them without any method behind that. They just put them together and that's it. So here I'm showing the results on one dataset collected from Twitter, where we are detecting sexist tweets. Healthy random is what we are proposing. So on the y-axis, you see different ways of ranking the examples. CDA and CDS are the ones that you have seen in the beginning. Healthy random is what we are proposing. And there are also some variations, unhealthy random and random. I will describe them for sure. And the y-axis is the improvement in fairness. So you can see that there is more improvement in fairness on both Bert and Roberta when you rank the examples based on the healthy random. Why is this happening? It's happening because you prune the harmful examples and you only include the important counterfactual examples. That's why you are outperforming the others. So let me just say what random is and what unhealthy random is. So let me go to the slide that I was using. So here I said what we are proposing is called healthy random, and it takes A% from the factuals and B% from the counterfactuals. The A% is just randomly chosen, and the B% are always the top B%. There is a variation that we came up with just to prove our point, which is what if I take the least important counterfactual sentences? So I know that when I take the most important ones, this is good, but what if I take the least important? So we call it unhealthy random, and we are showing that it's actually worse than healthy random. This is one variant. And there is also something that we have is called random, which is what if I just randomly pick up examples from the factuals and randomly pick up examples from the counterfactuals. So we are just trying to prove that this improvement that's happening is not random. It is actually something that is meaningful. So this is why we came up with those two variants, just to show that healthy random is still better than all of them. So there is a meaning behind the way we organize the examples. And of course, you have to look on the degradation and the performance. There is a degradation in the performance, but we promise that our method is not going to cause a degradation of more than 3%. So on different datasets and different models, our degradation never exceeded 3%. So there is always a trade-off. So when you improve fairness, there is a trade-off and there is a degradation in performance, but it is not more than 3%. We tried different datasets. This is from Wikipedia, and this is from Kaggle competition. Again, we found that healthy random is outperforming the other baselines on different models. And that's basically it. So I'm going to go to the conclusion, and of course, you can ask whatever questions you want. So we are proposing a method that is improving some of the parts that we think are not are kind of limitations to data augmentation. So we are improving two things. We think that it's good to add the counterfactual examples, but it's even better to prune the examples that are harmful. And the other improvement is that we're saying that you don't need to include all of the counterfactual examples. You only need to include the important ones. So we defined what exactly we mean by importance, and we are only including the important ones. And this is why we outperformed CDA and CDS on different models and different datasets. And this does not have more than 3% of degradation on the performance. So that's it for me. Thanks for your listening, and I'm ready to take questions if there are any.
Awesome. I'm going to stop the recording.